till infinity and beyond.
Post money.
Actually, they're on right now. They actually stream live. So like if you were home and wanted to watch, you could. Yeah. So I do that on my YouTube channel. Leave your likes and subscribe.
So you never have to come.
Technically, you don't have to.
You never said
But what?
What's your name? I'll subscribe to you.
It's just J Munoz Math. It's J Munoz Math. So we left the semester. Congratulations to everybody. You guys all did great. You look sharp. Get a haircut? Sorry, did you cut all your hair on your head? Looks good. All right, let's get started here. We kind of started this chapter 15 probability models. We didn't get through the whole thing, so I'm just going to go ahead and cover some of this again if I remember how to do this. I couldn't even send it to my computer this morning. I was like, yeah. But anyways, whatever. All right, so probability models. Okay, we talked about random variable, right? And a random variable we're talking about that, yeah, we are talking probability-wise. But something that you need to know about a random variable is that when we are talking about it, that's not be confused with like regular data that you collect. We use the capital letters like capital X or capital Y to denote these random variables. When we talk about a probability model, it consists of a collection of all possible values of a random variable. And I think we've done a couple of those charts, right? Where we have, what's the probability of getting 0 heads? If you flip 4 coins, we're probably getting 0 heads, 1 head, 2 heads, 3 heads, 4 heads, and so forth. And you can see the distribution right below that. That's what we're talking about, the probability model. Questions not up there, but let's see if you guys remember. How do you know a probability model is legit? Like it really works or whatever. Ah, nice. The sum of the probability should equal 1 because they account for all the different events that are occurring there. So they should equal 1. Here. So, and I know this might be a little confusing now at the bottom. We talk about a random variable having a capital letter, but then they talk about particular values or lowercase x. Well, let's talk about what that means exactly. So if I say random variable x, and I'm talking about flipping 4 coins, it's the probability, I could say that's the probability of flipping heads, okay? Now, when we talk about the specific values, we're saying, hey, what's the probability that x is actually equal to 1? Okay, so in this case, we're saying out of those 4 coins, how many times do we get exactly 1 head? Okay, so that's what we're saying. X is equal to 1. We're looking that out of those 4 coins, only one of them is going to be a head. You can also say, hey, what's the probability of getting no heads? Or getting 2 of those being a head, and so forth, so forth. Does that make sense? Capital versus lowercase. Cool frijolitos. May I continue? No, I'm just trying to gauge you guys. I forgot to not save. Okay, cool. We're good with this one, the probability model? Okay, cool. Expected values. I gave you guys a couple formulas already. We talked about expected value. Whenever you hear this word expected value, what's another easier way of making sense of that? Kind of like X bar, the average. Okay. When we talk about expected value, that's really what we're talking about. Is going to be the mean or the average of something. On your reference sheets, I think you'll see this for expected value, but don't be surprised if they don't have that, and then a capital X at the bottom. Noting that they're saying, oh, we want the mean of random variable X, therefore it's expected value. Y'all in the back? Over there. All right, cool. So, expected value. If you want to find the expected value, there's your formula. You should have already seen it. It's going to be the sum of all of the x's times their probabilities, right? So you take the first x, multiply it by its probability, you add it to the next, times its probability, next and its probability. That formula is given to you, so you should be good. And to make this easier on yourself, I would throw those into a list, and then just have your calculator multiply the two, and then find the sum of the column where you multiplied the two. But that is your expected value calculation. We're good here? Can I continue? Okay. No? Okay. Next formula they're going to give you is variance. Okay, it looks like this. And it's the sum of those differences squared on the mean with the probabilities of those. And then, of course, to get to standard deviation, you have to take the square root of that. Yeah, you should. We already did some of this, and I'm just kind of reviewing a little bit of it because we kind of stopped halfway through. But you should have this down. And yes, if you want to get standard deviation, you do have to cross variance. Okay, and so you'll end up getting them both anyway. Anybody have any issues with anybody really have allergies, like bad allergies? No?
Not today, no.
I've been having a rough time this week. It's okay, it's not just me then.
It's like right here in my throat.
I feel it like right up here, so I'm just like pressing on it so I don't. Okay. Bernoulli trials. Bernoulli, I think, has everybody heard of Bernoulli? I don't know his first name. We kick it on Fridays. But anyways, there's a specific probability set that's identified by Bernoulli. It's going to be called a Bernoulli trial. And it can only be a Bernoulli trial if there are only two possible outcomes. And, for the sake of it, we'll call those outcomes. This is new, so you should be taking notes on this. Those outcomes can only be a success or a failure. It either happened or it didn't, right? The probability of success, P, is constant for all of those, and the trials are independent. Okay? So if you're looking for a Bernoulli trial, you got those three conditions going on. And there should actually be another one, and I think it'll come up next. Okay? So those are three of them that are required. Go ahead. You feeling all right? No. No? I'm sorry.
I'm tired. We need a break.
Oh, hi.
I'm not even joking though. I've been passing out all day.
I see what you're saying. You got to get back in the flow in the mix, right?
Fucking stickers on everything.
You mind? Want the words?
I'm trying to get my new notebook. But
Yeah, but you're dropping profanity.
Can you hear us?
Yeah.
Oh.
So if I say what's up, and then I watch the video, I'm saying what's up to myself.
Yeah.
Streaming.
Yeah, go ahead and give yourself a shout out there, Bert.
It's like, hi.
Sorry, Mom. Put in the camera.
Where's the camera at?
The establishment is a joke.
Hello.
Down
Moving
with
on.
Big Brother.
Not really, dude. Come on.
All right, so, anyways. Sorry.
Screen capture.
Yeah, it's a screen capture with audio on it.
Point at the
I did have a camera. I took it off because people would ask to go to the bathroom and walk in front of it so they could come out. So I was like, I just stopped it. It was too much hassle. Plus, they say that it's 50 pounds. Just kidding. I don't know. But yeah, I think I have it at home. I'll bring it back. I'll probably use it for some other stuff. It's wireless cam, so it's cool. Okay, so when we are doing these specific types of events or trials, we don't really call them Bernoulli trials, even though that's like one of the technical names. I'm usually going to call them binomial distribution problems. I just kind of got used to that. Okay. So for a binomial model, it tells the probability of a random variable that counts the number of successes in a fixed number of Bernoulli trials. So, in a binomial distribution, we've got to meet a couple of conditions. We have to meet the Bernoulli trial conditions, which, what were they again?
Success failure.
Success or failure. It has to have independence. And the probability is constant. But now we're also adding for a binomial model one more thing. And what is that? Successes are fixed. Okay? And in order for that to happen, you have to have a fixed number of trials. Okay? If I do something 5 times, it's going to have a specific number of successes, correct? But if I make it 10 in variable, isn't that number going to change as well? So I need to make sure that the number of trials is fixed. Now, I'll give you guys a really cool tool, mnemonic, if you will, to help you remember those. And I know that no one has said, I don't like it. I hope it never happens. Something else you need to know, when we talked about normal distribution, the notation was n, mu, comma, standard deviation, right? And that's all the information that you needed in order to make mathematical calculations based on normal distribution. You needed the mean, and you needed the standard deviation. Any calculation that you're going to make for a binomial distribution only requires these two things, which is n and p. N is the number of trials, and p is the probability of success. Well, that's pretty cool, yeah? I like that a lot. I'll have to bring my neti pot to school. Do the neti pot?
Oh my god.
No?
I know what those are.
It's like a, you know what it is?
You can die.
You can die?
You throw a kind of water.
Really?
The wrong kind.
What kind of water?
Some of the thousand ways to die ones.
No, you scared me. Now I don't want to do it.
Well, I mean, anything that's like
really nasty tap water sent to their chest.
Because it can go straight to your brain. Okay.
anything that flows out of a reactor is probably fair game, though.
You know those like nasal port sprays? I had to use those so much when I was younger that I got like ulcers up in my nasal cavity. Yeah.
Not good.
It's not good.
Too soon. Alright, cool. So, I'm going to give you guys that mnemonic right now. Is that what they're called? Mnemonic devices?
Yes.
Okay. If you want to know if something or some trial that you're going to work with is a binomial distribution, then you need 4 things, yeah? And they're going to go like this. You're going to write bi, nom, I. Oops. I want you to write binomial like that. Bi, nom, I, all. And I know all is A-L, but I think that kind of helps you, doesn't it? What does bi mean? 2, which means, in our case, 2 outcomes, success or failure. 2 outcomes. And those are for us either success or failure. Okay? Nom. Nom kind of looks like num, right? For number.
Sure.
Num, 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 num. Num is going to be the number of trials is fixed. So fixed number, num, of trials. And that looks like a Z, not a 2. Somebody laughing at that earlier?
Trying to be street, Mr. Munoz?
Trying to be what?
Are you trying to be street? Are you trying to be down with the youth?
Why? What did I say?
No, I don't know, just kind of replacing random letters with Z. You know, like how they say, I can't think of an example, I'm sorry.
You know, one thing that happens.
All right. So bi is 2 outcomes, success, failure. Num is the fixed number of trials. What is I for?
Me, myself, and God.
Independence.
Independence.
Independence. Independence. Is it ENC or ANC? It's ANC? ENC? Okay. That would have been cool if it was independence. Because then, oh, then we can make a video on that, right? The independence, like the pineapple. No? Hey, welcome back. I know it's day one. You guys are a little chatties. You got a lot of stuff to do though. What is all for? All probabilities are constant. All PRBs constant. PRBs. So I think that's pretty cool. Helped me out when I was learning it. So binomial, does it have exactly two outcomes? Are all is it a fixed number of events? Is it independence? And are the probabilities all the same? Those are the four. Once you go check, then you should be good to go. Okay? And you would say, oh, I'm working with a binomial distribution. Okay? Anybody still need this slide? No? Moving on then. Okay. Do you guys remember this thing up here? We did that not too long ago, huh? And choose K. And choose K. And I gave you guys another way of writing it, didn't I, as well? And if you don't remember, it goes like this. N, K, but it's here. Let me kind of separate it for you. Same thing, it's N choose K. It's a combination problem. Okay? But what you have there for N choose K is the different types or the different ways that you can get some number, right? So if you have 5 choose 3, how many different ways can you do that? That number gives it to you. Or I should say, that piece in the front. Okay? For this formula, we call that the binomial coefficient, but it's that number that's at the very front. Okay, it tells you all those different ways. So the binomial coefficient, N choose K. Anybody ever do that, N choose K with Pascal's triangle? No? No one done that? If we have some time at the end, I'll show you guys. Pretty cool. It's pretty cool. If I have some space that comes up in a minute. Okay? Notice there's 2 other pieces here, right? And I'm going to kind of separate these out for you. I'm going to use some green this time. I want you to think of this as another part of the formula, or another component, and find the last piece as another component. So there's really 3 parts here, okay, in order to calculate a binomial probability. You need the binomial coefficient, which tells you how many different ways what you're looking for can happen. This one here is how many successes you're looking for. Okay? So P is for probability, and K is how many successes. So it's the probability of getting that many successes. Q is failures. It's failures. And N minus K is how many of those failures you're looking for. So what you're really looking at here is what's the probability of getting that many successes and the probability of that many failures. And I tried to do this formula in some problem that we had earlier, and it's not what they were looking for at all. So. And I'll walk through a couple of examples. We'll make them up. Oh, here's some vocab for you there. Same thing. N is the number of trials. P is probability of success. We'll call Q the probability of failure. If you have your formula sheets, thank you. If you have your formula sheets, please notice that it'll say this instead of Q. But whenever you see Q, because that's pretty adopted, that means failures, okay? So in your formula sheets, you'll see 1 minus P. It's the same thing as Q. And then X is the number of successes in the trials that you're looking for. On your formula sheet, it's actually going to be very different. Let me write it out. Let me find that real quick. Here, this is the way I remember it. And you guys can correct me if I'm wrong. It's going to read N, K, P, K successes, 1 minus P, and actually K is on the outside. K, 1 minus P, N minus K. Is that the same thing? Okay, they just put X instead of K. So the blue part, I'm pretty sure that's how your formula sheet reads, but it's the same thing, right?
Yeah.
Do you guys see that? Cool beans. Yeah, they used X instead of K. Huh? Cool. They're just saying where this piece of it is really this formula. Does that formula look overwhelming?
Yeah. A little bit.
It's really not. I don't want you guys to get yeah, can I get rid of this blue part? I'm gonna right there. Here's what I want to do. What am I gonna pick on? I'm gonna pick on wiffle ball. Never mind. What's your name again? I was gonna call you Kurt, but I'm not going back to that. I know you're Kurt. Caleb. Caleb. Caleb is a baller. Caleb is a baller. And when he goes to the free throw line, because he likes to, he does his free throws. The probability of him making a free throw, should we be nice?
0.
Oh, no, that's not cool. 65%? Reasonable? So the probability of him making a free throw, okay, because he got fouled, right? And he was actually shooting.
Wait, you don't get fouled on a free throw.
Whatever.
It's a free throw.
He's getting free throw. I'm trying to establish how many shots he's going to get.
Okay.
So he was making a shot and he got fouled. You get 3, don't you? Or is it 2 on that?
It's okay. It depends on the
Tell you what we're going to do.
Usually it's 2.
We're going to give you 5, dude.
What?
Because this is stats and we can do that. We're going to give you 5 shots. Okay? We're going to give you 5 shots to make some points here, okay? And you make 65% of your free throws. Everyone cool with that? So he makes 65% of his free throws. He gets 5 shots. Are we working with binomial distribution? Did we meet everything so far? I want to make sure we do. So he can either make the shot or miss the shot. So it's got 2 outcomes, right? The number of trials is fixed. Yeah, I said you're only going to get 5 shots, so it looks like we're good. What's the next one? Independent. Does him making 1 shot affect the other shot? No. So they're independent. And then finally, we know that every time he shoots the ball, he's going to have a 65% chance of making it, right? Okay, so cool. Huh? Well, we're not worried about that. We don't even need it because we can calculate Q with P. And that's why you only need N comma P for a binomial distribution. Okay? So I can ask you a question now. What's the probability that Caleb actually makes 3 of those shots? That he makes 3 of those shots. Right? So I need to use that binomial formula. And I'm going to show you guys. Please just watch what I'm going to do because it's going to be easier to understand what the formula is doing for you. Okay? First, I need to figure out how many ways he can make those 3 shots, right? Because he can go the first 3, miss the last 2. He can go make a shot, miss a shot, make a shot. All those different ones, correct? So I'm going to go 5, choose 3. That's the first part of the formula. Simple enough? Okay, next part of the formula. It's the probability of success, which happens to be 0.65. I need to take that to some exponent, And that exponent is going to be, how many successes I'm looking for? It's 3. I want to see how many he can make, so I want 3 of those. That means he's got to not make some, correct? So what's the probability of him missing it, the shot? 0.35. And how many do I want him to miss? 2. There's the whole formula for that specific question. That makes sense now? Because that's all it's really asking you to do. It's just all these little mathematical formulas, but that's all it's really doing. How many ways can he do it? How many successes am I looking for? How many failures am I looking for? That's it. Simple enough? Yes. Once I put that in my calculator, calculate all that, I'll know what the probability of him making exactly 3 of those shots is. Okay? Easy enough? Awesome, awesome. So how would that formula change if I said, hey, I want to know what the probability of him making 4 of those is? What's going to change? Does the coefficient change? How? Now it becomes 5 choose 4, doesn't it? So it's going to be 5. That's horrible. It would become 5 choose 4, and that's still a horrible 4. Does this part change?
No. Yeah, the variable.
Yeah. Variable.
The exponent, I mean.
The exponent will change to 4. Do I even need the 1?
No.
But I could put there just for the sake, just because. Okay? Make sense? All right, cool. So pretty simple, yeah? Yay! What's up? Yeah, go ahead. All right. We're still going to use Caleb's example because he's a baller. Okay? He gets his 5 shots. And that's it. After these 5 shots, the game would be over. Okay? And we want to know the probability of winning. In order for us to win, he needs to make 3 or more of those shots. 3 or more of those shots. That changes, doesn't it? Okay? So here's what I'm looking for. I'm looking for the probability that x is greater than or equal to how much? 3. Yep. So how would I do that one?
Would you take the probability of 3, 4, and 55?
Exactly. Correct. So I would have to do 5, choose 3, not 0.3, I knew I hit something, 0.65 to the third, 0.35 to the second, plus 5, choose 4, 0.665 to the fourth, 0.35 to the first, plus 5, choose 5, 0.65 to the fifth, 0.35 to the 0.
Which is just 1.
But the sum of all those would be the probability of him making 3 or more shots.
So you just do 1 for each of them? Or?
Correct.
Okay. That's not bad.
Okay? And it's not bad. I mean, it does get bad when you have like 20 trials.
Right now, it's okay.
No, but that's what I'm saying. I just want you to understand what's happening. And it makes sense, doesn't it? Yes? Anybody have questions on any part of this? Meryl? Is it making sense? No? No, I've got YouTube. You can go ahead. I feel horrible. I want you to rest. No, you're not fine. I shouldn't have even said your name. I'm sorry. I'm a horrible person. Okay. If you want to find the mean, Dana, the average of a binomial distribution, it's simple. It's n times p. Yeah. Yay! But it's not going to work because it's still processing the other video.
Wait, does that mean that this part of the video isn't going to show up?
Probably not.
Oh.
Probably not.
Probably.
Probably not. Let's find the probability. Wrong scenario altogether. Wrong scenario altogether.
It's like when your friend says bet and you know that neither of you got money.
Way to be a better student this year.
Oh shit. We know some paying attention. I can watch it. I'm sorry.
Okay. Dana, do you still need this slide? Okay, change it.
I'm gonna come in with notes tomorrow. You'll see.
All right, cool. Now let's go back to independence, okay? Independence. Okay. Make note of this 10% rule. It's going to come up a lot, okay? Because usually we've been given the easy definition of if one does not affect the other, it's independent, which is true. But sometimes when we have very small samples, we really can't say that they're independent, okay? And so there's a couple ways that you can kind of see this. This is called the 10% rule. But what I'm going to have you do to figure out whether it's independent is to take 10 times the sample size n. Okay? So if the population is greater than or equal to 10n. So let's say let's make something up. I've got 50 pretzels and I want to see how many grains of salt are actually stuck on them. Type of thing, okay? I don't know, it just came to me.
It's funny.
It happens sometimes, okay? So I've got 50 pretzels, right? I would say, all right, I've got 50 pretzels. I want to know if they're independent. What's 10 times 50? 500. Now you ask yourself, oh, that's not 500 at all. That's like 500. So you're going to ask yourself this question. It's a very important question because I've got a number now that I can relate to, right? Are there more than 500 pretzels out there?
No. In the world? No. Not any.
Surely there's more than 500 pretzels, right?
Not any.
So that's what you'll say. We're working with 50 pretzels. Surely there's more than 500 pretzels out there. It's the same rule, right? But I'm not calculating what 10% of the population is because I don't know what the population is, right? Do I really know how many pretzels are out there? How do I know I've got less than 10%? But it's easier if I do some algebra and I mess up with that formula and I just go 10 times n. Okay? And I multiply. So I'll say, oh, I'm sure there's more than 500 pretzels out there. That's a much easier conclusion than say, I'm less than 10% of the population. Did that make sense? Kind of, sort of?
What does it matter if it's less than 10%?
What this is saying is that if the sample you're working with is less than 10% of the whole population, then you can say that you have independence. But it's hard to calculate 10% of something when you don't know what that total is, right? I mean, how many pretzels are out there in the world?
No.
I don't know. There's only 7, and I hold 2 of them. My dad has the others. It's a patented. They're made of gold. So it's easier when you look at it this way, right? I'm going to take my sample and I'm going to multiply it by 10 instead of dividing, which is what you would do, and then I can make a conclusion based off of this number. And I'm pretty sure there's more than 500 pretzels. I'm pretty sure there's more than 500 pretzels in my house right now. Seriously. So my kids like pretzels.
What kind of pretzels?
We have the regular ones, and then I have some sourdough pretzels.
You mean like the little
The ones you buy in a
sourdough
big bucket from Costco.
I mean like
The
the little
what are they called?
sourdough nuts.
Mutts or something, or nuts or
I forget
nuts.
what-
Nuts. They're nuts.
I'm still calling them nubs.
Nubs? Okay. Questions on the 10% rule? Cool beans. Pretty simple stuff. So here's that condition, okay? As long as your sample is less than 10% of the population, then it's okay. So whenever you're doing that binomial, right, under independence, make sure that you check that condition by doing the math part of it, okay? So let's go back to here. Let's not? What? Oh, sorry. Were you still writing? Where was I? Here. So let's go back to Caleb's example. Caleb had 5 shots only, right? That's pretty small. So could we say that those are independent? Okay. Now, if he's a basketball player, truly is. Surely he's shot more than 50 free throws, right? So I could say that. Surely he's shot more than 50 free throws. Therefore, these should be independent. Cool. Cha.
I was so confused. I didn't know we were talking about basketball. I'm like, what?
Welcome back.
Space Jam players and Dist.
Dana, we good with this slide? Okay. Normal model to the rescue. Binomial problems sometimes cover too many options. But when a binomial problem grows so big that sometimes it's, when it's really, really big, that sample size gets really, really big, we can approximate a normal distribution. Yay, normal distributions, right? So once we get our numbers and stuff, we can go in and we can use that normal table that we had and make calculations off of that. Here's your normal condition, okay? And this should kind of make sense. You need to have more than 10 successes and more than 10 failures. Okay, and the way you calculate that is n times p. And then n times q. So how many successes do you have? So so if we're looking at Caleb's example, it was 0.65 times 5, right? Well, obviously, he didn't have more than 10 successes or 10 failures, correct? Because he only had 5 shots altogether. So could his distribution be normal? Not at all. How many shots would we need Caleb to take in order for it to be considered normal? 20. And 20 is not it. I know that was the first instinct, but it's not. Well, we have numbers, right? What's the probability of him making the shot? 65. So I'm going to use some math in here. Okay, n times 0.6, that's a horrible 6, is 10. So if I divide both sides by 0.65, I would get the number of trials that we would need for this. So what is that? What's 10 divided by 0.65? 15 point what? 0.38. And then we would go over here and figure out the number of failures. So it would be n 0.35. So what's 10 divided by 0.35? 28.57. So let's add those up. Add those two up. Round it up. Round it up. Don't round it down, because if you round it down, then you would be below those levels for either one of those. So we would have to. So in order for us to consider his distribution to be approximately normal, you'd have to take 44 shots. Does that make sense? Yeah. Good. Cool. Go algebra, right? Yay! I can do that, man. Why are you thinking about a chicken? Wheezy and fast. Okay. Statistically significant. Statistically significant. Some things you want to ask yourself when we're talking about statistically significant. When is something unusual? And we've had that conversation, right? When does it cross that line that we say, something fishy is going on, or it couldn't have just happened by chance alone? Okay? So when is something unusual? When is something likely to happen just by chance? Now we're in the position to finally answer that question. Roughly speaking, when we're using the normal model, now we can use our table, right? And see what those probabilities look like. And yes, we will be doing more on statistically significant, some more concrete numbers that you can calculate. But for now, I think once we go to normal table, get a probability, we can say, oh, that's not very likely to happen. Correct? You cool with this slide? Yeah. I'm going to wait a little bit. And enjoy this job.
Say Java.
Java. Okay. I know you guys are done when you start talking. Here we go. So, what can go wrong? What can go Probability. probability models are simply that. They're models, okay? You can't really predict what's going to happen, but you can have a pretty good idea of kind of, I don't want to say the odds, but you know, how often it should happen. Does it mean that that's what's going to happen? Not necessarily, okay? It could turn out that instead of making the 3 shots like we thought he would, he actually made 4 shots, okay? So these are just models, so maybe we guessed incorrectly. Because no decisions are ever made with 100% certainty. Bernoulli trials, make sure that you're using those rules, okay? And how many rules does Bernoulli trials have? 3, and if it's binomial, you're going to go 4. You need to include those Bernoulli. And what are they? What are those?
2 definite outcomes, success or failure.
Two outcomes, success or failure. Fixed number of trials. They're independent. And how do I check for independence?
Population standard.
10% rule, which we can take 10 times our sample size and see if there's more than that, right? In the population. And then finally, all probabilities are fixed. Are also fixed. So they should all have the same probability of happening, okay? Don't assume
Was that it, or?
no, people are talking and I don't want to be rude and interrupt the conversation.
I'm like,
Because we're working in a textbook, Mikey, a lot of stuff turns out to be nice. And math isn't always nice. So don't assume that every problem you work with is going to be normal distribution. Okay, make sure that you use at least 10 successes and 10 failures rule to check for that. And of course, here's what we've learned. You guys can go look at the video for that. And we're done.
sweet.
Off with your head. Question?
How do you check for normal on it?
Check for normal? You check for normal if there's at least 10 successes and 10 failures. So if we're talking about,
Inception.
I want to go to, where am I trying to go? There we go. So I'm going to try to write here, okay? Let's say I had, thank you. Thank you. So I'm checking if, because I've got an old box of light bulbs or something, I don't know. So I've got a box of light bulbs. There are about 50 bulbs in there. And the probability that they're not broken is a 0.53. So I'm calling this success not broken. Okay, the question is it a normal distribution or not? So what I'm going to do is I'm going to take 50 times 0.53. What number is that? Well, a little bit more than half of that is more than 25, right? 26.5? 26.5. So this one checks. Next I check the number of failures. I've got 50 bulbs. I'm going to multiply that by 0.47. So what's 0.47 times 50? Point what?
23.5.
Awesome. 23.5. Are both of those greater than 10?
Yeah.
Then this should be a normal distribution approximately. And I can go through and use my normal tools. Any other questions? Thank you. And here's the formulas real quick. N times P should be greater than or equal to 10. N times, sorry, that's not N. N times Q should be greater than or equal to 10. So that was normality. Other questions? Dana, we're good?
Homework, question mark?
Okay.
I have not written anything. Don't have